Okay, so I will start the ODE solvers. So needless to say that ODEs are the backbone of science. Physical universe, the description is through differential equation. You assume time is continuous and it seems to be okay till good approximation. We don't know whether time is really continuous or not. But so ODEs are very important, and many equations are nonlinear. Okay, so you are aware of nonlinear, no? So most nonlinear equations you can't solve. So then you have to resort to numerical scheme. So it becomes very important for you to understand how to solve numerically. Okay, so let's start. So I am going to use the following notation. My x is a dependent variable, unlike the last class. So let's just use that. And t is my independent variable. So like mechanics. So just think of x as a position and time is a time. T is time. So one equation I can write is for the velocity dx by dt is some function of x and t. Okay, so we will try to solve this. So we can also call it x dot. Is shorthand useful notation. So we would like to solve this equation numerically. So some of them have exact, well, first order equation has exact solution, but we want to solve numerically. So the idea is that suppose I am at xn at time. So let's divide time discretely. So time, it need not be even. So this need not be evenly spaced, but first I am here Tn and I want to go to Tn plus 1. I want to find x at Tn plus 1 given my position or x at Tn. And what is given to me is this. So it's a velocity, okay, if you want to think of in mechanics. So you are given f, which is function of x and t. So idea would be, so I will have to redraw this again. So let's draw t and x. So this is my Tn and Tn plus 1. So my real function is going like this, suppose something like this. This is really is happening with the physical system. So at this point I know the slope. So by the way, I don't know what this is. I have to numerically compute it. So what I could do is slope, which is f. So I compute the slope here, or I compute f at that point, and using the slope I extrapolate till here. So at this point I extrapolate and I reach here. So this is not the exact, this is not the correct value. The correct value is here. Had the function been linear, I would have reached there, but function is not linear. My x, not, by the way, this is not f, this is x. It is not linear, so I reach here. So this is called forward scheme. So this is xn plus 1 forward. So I go, so I am sorry, is it blocked? Some people can read this or no? So this is x forward and we call it xn plus 1. Now, so this is forward scheme. Now we say, well, I mean look, there is a lot of error, right? So I don't like that. Let me use this point and slope here. Of course we don't know that point, but imagine for some reason or for equations which I am going to solve today, they are toy equations, they are not really the real equations. Suppose I know the slope here, then I can use this slope to extrapolate from here, because I have to go from here. This is my present position. So I use this slope, so parallel to this I reach here, which again is underestimate. I am not able to reach my correct value, but this is called backward. So x backward n plus 1. Well, somebody says, well, this is all, none of them look good. So let us use the midpoint. So what we will do is, so somebody says, well, some region, suppose somebody gives you the slope in between. So I can use this slope, which is this slope. I use the interpolation from here to that. So this parallel line you draw, I do somewhat better. No? So if I choose a midpoint, I am doing better. So you can use this using the midpoint. This with midpoint. So we have to compute f. Now this is, you can see, is a chicken and egg problem. I don't know my midpoint, so I can't compute f. So I really can't do neither this scheme nor that scheme. But there are ways to, well, the idea is that you go make an estimate of the midpoint. Because these are the tricks, you know, and the very cute tricks people have devised, and you try to do as good as possible. One can also do average of the two slopes. So this slope is doing overestimate, this slope is doing underestimate, so do the average. Okay, so that's like trapezoid rule. Okay, so these are various rules. So let's try to write a formal way to how to solve this. So formally I should write this as xn plus 1. So I just integrate this, no? So xn plus 1 equal to xn plus integral fxt dt. Or let's write like this, equal to this. Now I have to estimate this. So one way to estimate is that, now I am going to write down all this stuff. So you say, well, f at xn tn multiplied by h. So that is a stepping, no? So use the slope and multiply by h. So this is that estimate of the integral using the value of the f at this point. Now since it depends on xn as well, that is a problem. If it depended only on time, no problem, then I would have coolly done it, but it depends on x, because x, I don't know the future x, that's my issue. So this is forward scheme, or you can say h, value of the function at x n plus 1, and of course you have to put time also at t n plus 1. So this is future, so this is called backward scheme. Or you could have xn plus 1 minus xn h midpoint. So midpoint will be f of x, we write it as n plus half. N is my time index. Okay, so n is my time index. N plus half, t n plus half. Or, so this is the midpoint scheme. Or I could use trapezoid rule, which is average of the two slopes. So h by 2. So this is called midpoint method. F xn tn plus f x plus 1 tn. Is that clear? So this how, in fact I am using my ideas from integration schemes. It is another nice way to say as well, here I am using only 2 points. Now this is the integration of the function between using 2 points. Suppose I had 3 points. So I have point tn minus as well. Then I can use, in fact I have better estimate. So my integral will be going from, so I can write this as xn plus 1 minus xn minus 1 is equal to, now let us imagine that the h is equal, h and h. So 2h, so what is the rule is called? So 3 point is a Simpson rule. So this is f of x n minus 1 t n minus 1 plus 4 okay. So that is, so there is one issue here that I am jumping from n minus 1 to n plus 1, not from n to n plus 1. So this method has issues, it's more accurate, but the problem is that I am making 2 jumps. So one has to be careful with this scheme, but this is Simpson. Now, so these are all nice, you can start coding it and trying to solve it. This scheme is called the whole thing, this is called Euler scheme. Okay, Euler, famous mathematician Euler. We will discuss this bit later. Okay, they have names, but so let's focus on Euler. Euler forward. Now, somebody may ask, so let's just try to keep it simple, very simple, so that I can get exact formulas and see how good is my Euler scheme doing. So the example I am going to use is x dot equal to alpha x, whether alpha can be positive, negative or complex. I will allow all possible alphas. So according to this scheme, forward scheme, Euler forward, so I will get xn plus 1 equal to xn plus alpha xn. Okay, so this is h times alpha xn, h times f, computed at point xn. So this is exactly solvable, alpha h. Whether this is also called recurrence relation. Okay. So given xn, I can find xn plus 1. Now I can put this in a computer and crank it. So typically you are given x0 somewhere here, t0, and you time step, equal time marching or time stepping. So this is a technical name, time step or time march. Okay. Now, so this is my approximate value. So what is the error? So you can estimate the error. In fact, you can estimate error for arbitrary f. What is the error in this scheme? So let us do it for arbitrary f, and we will say that this is, we will compute what should be the formula for here. So I am going to do it by Taylor series, xn plus 1 equal to xn plus h times, so I am expanding from at this point, Okay, so my formula, please remember, I am trying to solve x dot equal to fxt. So I am writing this as x is my function. So x t plus tn plus h, that is xn plus 1, will be xt, this is xt, this is xt. Now Taylor series, what does it tell you? Next term is hx dot, right? That is a Taylor series. Next will be h squared by 2 x double dot. It's function of time, so we just try to do it, plus higher order term. Now this term is what? X dot is f, so I compute this is f, but my error is here h squared by 2, and x double dot is what? I have to take the time derivative of this f dot, but then it is function of x and t as both. So, I have to write this as delta f by delta t plus x dot delta f by delta, and x dot is f again. So, given f, I can compute any derivative. I have to just do it again and again. Okay. So, this is my error. In Euler scheme, which is S squared is a bad scheme, something which is just is accurate only up to linear order. So, any function which is quadratic is not good. So, this is single time step. Suppose I go from 0 to capital T in n steps. So, it is going to t times t equal to capital T equal to n times h, correct. I divide into n steps. Of course, sometimes errors can cancel. So, this thing can come with different signs, plus minus sign. But suppose worst case scenario that they all add up. If they all add up, my error will be adding up. So, error will be s squared by 2 max of x double dot multiplied by n. It is less than equal to. I should put mod of this. So, I am putting a bound. So, this is nh is t, so t times h by 2. So, something linear in h. So, h I may take 10 minus 3 and my answer is order 1. So, I am getting accurate only up to 0.1%, which is not good. Okay. So, if t becomes large, then it becomes worse. Suppose I want to go to t equal to 100, non-dimensional time. Again, I am talking about non-dimensional time. T is 100, 100 times h is 0.10 minus 3, so 0.1. It's like 10% error. So, accuracy is very bad for Euler scheme. So, this issue is called accuracy, and you can make an estimate of accuracy by doing Taylor series. So, this scheme I will describe that this scheme is better, is order h cube, is accurate up to order h cube. Both these schemes are this scheme is h cube. So, we have to devise higher order schemes. Okay, so this is for accuracy. So, we will discuss it when we discuss better schemes. So, for your project you should not use Euler, even though we emphasize Euler for illustration. Euler is not the scheme you should use. We will describe Runge-Kutta scheme which uses this scheme. Well, uses this scheme, not, I mean it is part of it. Okay, Runge-Kutta is not exactly this. Okay, so I will describe those schemes, and you should use at least Runge-Kutta second order. Runge-Kutta fourth order is better. Okay. Now, so this is about accuracy. Now, there is very important point called stability. So, how do I test stability? So, we are aware of stability in mechanical system, no? System is stable. So, if I take this raw chalk like that, it's unstable, but if I keep it like this, it's stable. So, stable systems are, if I displace it from my equilibrium position, it will try to go back to equilibrium position, and unstable systems are one which is, if you displace it, then it will go away from the equilibrium position. But it turns out for differential equation that is not a definition. Definition of stability is very different and is very critical. You may not worry too much about in this course, but you should worry about it, especially for your research projects. You need to worry about it in this course. If you are doing PDEs, stability is an important criteria. So, how do I define stability? So, let us again look at this example, x dot is alpha x. If alpha is greater than 0, then the solution of course grows with time. So, xt x0 it grows with time. What if alpha is less than 0? Solution goes to 0. So, if my physical solution is growing, and my numerical solution should also grow, but you may call this as unstable system, right? And in fact, this is called unstable system in physics, but we don't call that unstable in numerical scheme. Both, so you are talking about numerical stability. So in numerical computer, this is, we don't talk about stability, we don't call this unstable. So what is unstable for computer scheme is if, so let me just write down from here. So a method is stable if it produces a bounded okay, is that clear? A solution is stable if it produces a bounded solution when the solution of the differential equation is bounded. So you have to test for this solution. So if a physical solution is bounded, it in fact goes to 0, but if a numerical solution starts oscillating, then the solution will be called unstable. And of course, if my numerical scheme also goes to 0, then it's stable. Now there are some corollaries to this, some definitions which you also should remember. Conditionally stable. So when is conditionally stable? When solution is stable for some, unstable for some. So I'll show you some examples. Okay, I mean this in fact will use the same equation, and I'll show you. So it's stable for some and unstable for others. You can also call it conditionally unconditionally stable. So that means stable for all parameters. If it's stable for all parameters, it's called unconditionally stable. Unconditional support, you know, you just give unconditional support, or unconditionally unstable. So it's unstable for any parameter. So in fact, schemes are one of the three. Is either is conditionally stable. So conditionally unstable is same as conditionally stable. Okay, or unconditionally stable and unconditionally unstable. Now let's see whether, what about this equation? So let's look at so Euler scheme, x dot is alpha x. So I showed that my equation is x n plus 1 is so the stability for a scheme. So I am talking about Euler forward scheme. So it's not, I mean, so every scheme will have this analysis. So now for alpha negative, so remember, so we have to test only for alpha negative. Alpha positive is both schemes are, I mean numerical scheme you don't say anything, my numerical solution will grow and my physical solution will grow. But for alpha less than 0, I have to check. What about this term? What happens to this? For alpha less than 0? So can your solution oscillate? No? Solution can oscillate or no? Will it always go to 0? So when will it not go to 0? When alpha h is greater than 1. Now we can choose of course h so that it becomes greater than 1. So this unstable if 1 plus alpha h is greater than 1. So I mean alpha, so imagine alpha is minus 1. So just to give you a trivial example, minus 1. So if I choose h is your choice, h I could choose as 3, h is 3. Well, you may laugh at it right now, but you will find situation you will make a mistake. I will show you an example where whatever h you choose is unstable. For this is a trivial example of course. So here h nobody will choose as 3, but you use h equal to 3 here, then it is unstable. In fact solution will, so it is going to, so if you choose let us say alpha is minus 1 and h is 3, is going to do like this. In fact it is going to grow. You keep switching sign. So it is unstable if this condition is there. Okay. So this system, Euler scheme, Euler forward scheme is conditionally stable. That means for this condition is unstable, stable, okay, and of course if this is 0 then is equal to 1, then is not correct, the system remains constant, which is again not true. It should either go down or go up. It should go down. In fact I should say this equal to 1 is also, unless you choose your starting point as x equal to 0. So Euler, so that means that my conclusion is Euler forward is conditionally stable. Is that clear to everyone? So let us do a slightly different example. So I am going to use, instead of x, z dot alpha z, but z is complex and alpha is also complex. I use alpha as I pi. So this example from Fergier's book, minus I pi. So what does the solution look like? Solution is oscillatory. So zt is the same solution, no? Z is complex. So z0 e to the power minus I pi t. It is oscillating. It's a imaginary, it's a complex number, but it's going on a circle in the complex plane. So it's going on a circle in the complex plane. So what happens? Yeah. Solution will what?
Bounded. I mean it will stay constant.
That's true.
So stable, in that case would it be stable?
Yeah, so okay, it's a good question. So my answer is going to 0. Well actually maybe, yeah. So I think I will grant you that. I will just erase that. So if you start from 0 I get the correct answer, but if you start from something else I stay there in the non correct answer. Okay, so you are right, it is bounded, so it should be stable according to the definition. So in fact, so you should put equality here then, right? Okay, so now what about this? So is the Euler scheme stable or stable? Conditionally stable, which category? My solution is changing with time. Now the formula, this formula is still the valid formula. Instead of x I have to write z. So zn plus 1 is 1, alpha is minus I pi, 1 minus I pi h zn. So now what is the condition for stability? Now this is a complex number, no? So I can't simply say plus minus, you know. So mod, you have to put the complex mod. So I have to put a mod 1 minus I pi h mod. So, if greater than 1 is unstable. So, is it true or not true? Is this quantity always greater than 1? Yes, it is a complex number, it is purely imaginary. H is always positive, okay, H cannot be negative, H is always positive. So, this is square root of 1 plus, so it is always greater than 1. So, the system is unconditionally unstable. So, it is a problem with Euler scheme. Euler scheme, for whatever H I choose, my system will grow. So, I will illustrate all this numerically in the next class, but this is bad news. Euler scheme is, that is why Euler scheme is not a good scheme. We can write down, so this for particular alphas, this is particular alpha, this alpha is positive, but this condition we can write down in terms of, you can sketch it in terms of arbitrary alpha. So, what the condition will be? So, I want to draw alpha h real, alpha h imaginary. So, I am demanding that 1 plus alpha h is less than 1. So, what does it translate to alpha h? So, to see that, let us think only on the real line. So, on the real line is going to be 1 plus alpha h is less than 1 but greater than minus 1. So, alpha h is greater than minus 2, less than 0. On the real line, it lies between minus 2 and 0, and is a circle with center minus 1. So, this region of stability is this. Okay. So, this is the region of stability for Euler scheme. Of course, my equation is of this sort. Now, there is a variation that you solve it in a real space. So, you can write down equation for x and y. So, that part is there in my notes, but I will not discuss it. Okay. So, this illustrates you that you can work in 2D with x and y, and again worry about eigenvalues and which eigen direction does it grow. So, all that can be done. So, even though I am working right now with one equation, but this one is really two equations. Now, let us think of slightly complicated example. X dot is minus 2xt, still linear. Is it linear or non-linear? It's linear in x. The t is the coefficient. So, this is a linear equation. So, this is 2t is a coefficient which can be function of time. Now, this equation has the exact solution. So, xt, I will not derive it, but minus t squared. Okay. So, if I just substitute, just verify this. So, if I substitute, it is going to be x0 minus 2t exponential 2t squared, which is same as that. Okay. So, this is exact solution. Now, is the system stable or unstable? Now, how do I verify? I want to apply Euler forward. So, again the same formula, but I have to be a bit careful. So, xn equal to xn plus h times minus 2 xn tn. So, h times f is this. So, this is going to be xn 1 minus 2 h tn. Now, this is my, so if I write this way, so you demand that this must be less than 1 mod of this. Is it always true? So I may choose very tiny h, but for large enough t this can become a problem, no. So you may think that h, I mean look, so if you are not careful your solution will behave properly in the beginning, but later on it will start oscillating. Okay. So one has to be careful. I mean stability is not a trivial thing, stability requires analysis, and this is of course equation is simple, but when you have higher order schemes I will not do much of in the class, but you have to do it if you are working on this kind of issues, you have to work out carefully. Okay. So another equation is, which is there again from Furgezer, I just modified it a bit. This equation is again similar form, so it also has exact solution. It turns out first order equation you can always write exact solution. Okay, first order ODE, there is a theorem. It could be very complicated, but you can always write it. You can integrate first order equation. So this one, it turns out that it is exact solution. xt is x0 t squared. Now what about stability of this guy? xn plus 1 equal to xn plus h minus this one 2 xn squared tn. I just put f, but at that point. So this is xn 1 minus 2h tn xn. Now now you can see from the solution, since I already know the solution, I can reduce something. Now this of course grows, tn will grow, but xn drops faster than tn, where there is t squared sitting here. So it turns out this guy always will be bounded, we choose appropriate h. Okay. So this system is for, of course if you use h, very bad h in the beginning itself it will become unstable, but if you choose proper h then this system is stable, even though tn is growing. So this system is conditionally stable, of course it is not for all h, but you can rely on Euler's scheme, it will give you at least stable solution. What about the accuracy? So I will show you in the next class when I do all that numerically. All these systems are not very accurate, because error is of the order of h or h squared per step, h order h per in the full time scale. So you will find that the numbers are very off. So but one thing you definitely want is stability, and of course we like accuracy, so you need to work on both angles. Now Euler's scheme is unstable, but Euler forward scheme, but can we make some amends so that I can recover stability? So the idea is, in fact there is only small tweak and your system becomes very stable. So let us think of Euler backward scheme. So what is the Euler backward scheme? xn plus 1 equal to xn plus h, function calculated at n plus 1 tn plus 1. Now of course the problem is I do not know what is xn plus 1 in general, but for this example, which is a very simple example, x dot equal to alpha x, no, this is a very simple example, but it is good for illustration. So let us plug it in here and see whether this system, Euler backward scheme, is stable or unstable. So xn plus 1 is xn plus h is going to be alpha what? xn plus 1, not xn. Okay, so this is xn plus 1. So this is computed at n plus 1. Is that clear to everyone? Now I can easily solve xn plus 1. So what is xn plus 1? This implies xn plus 1 is xn divided by 1 minus alpha h. Now, is this equation stable? Now, remember problem is when alpha is negative. So, is this equation stable or unstable for alpha negative? What is it? Alpha is negative. So, whatever h I choose, this quantity is less than 1, right? Is guaranteed to be less than 1 as long as alpha is negative. So, for alpha negative, this object mod is always less than 1. So, this conditionally stable, sorry, unconditionally stable, is stable for all h. So, this unconditionally stable. Yeah. So, Euler backward scheme at least has one advantage, that it is unconditionally stable. Accuracy is again a problem, but it is very stable. So, the first one, this one will be stable. What about this one? When alpha is a complex number. So, suppose my alpha is minus I pi. What happens? So, this factor is 1 divided by 1 minus becomes plus I pi h. What about this guy? He is also less than 1. So, he is also stable. Okay. So, it turns out it will my oscillation, when I do the numerical solution, you will find that this will go in, okay, but it is stable, it is not growing. So, this is also stable. Okay. It turns out even these guys are stable. So, we can work out this one or both. How will you solve this problem with Euler backward scheme? So, Euler backward scheme will correspond to, let us solve this one this one. So, Euler backward scheme will be xn plus 1 equal to xn minus h, plug in my f, which is minus 2 xn plus 1 squared Tn plus 1. Now, so this becomes xn plus 1 equal to xn minus 2h Tn plus 1 xn plus 1 squared. Now, is it possible to solve like this? Now, this is Euler backward. How do I solve it? Sorry? Okay. So, this one you can use quadratic formula. I can be a bit nasty and I say, well, what about change this to kx power 5? Then what do I do? So, then I really do not know how to do it analytically, but then I can apply iterative scheme, which is one of the exam questions. Actually, exam question was not that difficult, exam was just iteration, but you can iterate it by trial solution. So, this is called Newton-Raphson. I am not sure you have done in your earlier classes. One of the iterative schemes, you start with some guess and you iterate it and you reach the solution. So, one of those schemes are useful. Of course, you have to choose a right guess and right scheme. If you do not do the right scheme, you may run away to wrong region. So, these are solved by iterative schemes. Actually, so in fact, so let me just mention one more scheme, then I will stop. So, you see the advantage of, in fact, these are called implicit schemes. So, let me just write this word. So, my solution is in terms of solution itself. It is like integral equation in quantum mechanics. So, these are called implicit schemes. and these schemes are called explicit schemes. So my solution is in terms of xn plus 1 in terms of xn, so it's explicit, but my xn plus 1 here is in function of xn plus 1 itself, so it's called implicit scheme. So implicit schemes are typically more stable, and so we'll come when you do PDEs, I'll tell you that you need to use implicit scheme for stability. So I think I will stop at this point, and then we will I'll illustrate first by simple codes, and then we'll do higher order schemes like Rangakutta, trapezoid rule, so we'll do all that. Okay, so I'll stop.